Hi guys, so today we're going to be looking at 5.6 inverse of a function part 2. So we're going to start off first by talking about the horizontal line test. Let's say that we have two functions shown to us, and I want to identify, is the inverse of these two functions an actual function? So I can write here, would the inverse of these graphs be a function of these graphs be a function? Okay, so the way I could test that out is by doing the horizontal line test, where if I were to draw a horizontal line anywhere on my graph, it should only intersect once on the image. For example, for the x to the power 3, obviously, if I were to draw horizontal lines, each time I draw a horizontal line, we get only 1 point in the end. There's never a time where we'll get 2 points. So this would be considered a function if it was an inverse function. So this would have an inverse function. Okay. If I were to do the same thing to this image right here, our graph intersects our horizontal line twice. And so if it intersects the line twice, we can't consider the inverse of this graph to be a function. So the inverse would not be a function. Done. Okay. So let's say that we asked to find the inverse of a cube. Let's say we're asked here to consider the function of f of x equaling to 2x to the power 3 plus 1. And we're asking to determine whether the inverse of f is a function. If that's the case, then we want to find the inverse as well. So I'm not going to draw an actual graph of f of x equaling to 2x to the power 3, but I do want to draw like a general sketch of it, just to see what it would look like. So if I draw a general sketch, I know that my graph here, the parent function, is f of x equaling to x to the power of 3. And I know that based off of the 2, we're going to stretch it, and it's going to move up 1 point. So if I were to draw like a general sketch, it will look similar to this, and it goes down kind of like that. And it's just going to go a little bit higher on the graph, but doesn't really change much about it. If I wanted to try out the horizontal line test, it looks like we're not going to get any issues here. All of our horizontal lines intersect once, and so I can consider the inverse to be a function. So the inverse is a function, which in the end makes my life a lot easier. Okay, so all I'm going to do now is when I find the inverse, I'm just going to go through the same steps that I usually do when finding the inverse of a function. So I'm going to start off first with y equaling to 2x to the power 3 plus 1. I'm going to swap out my y for x, so we get 2y to the power 3 plus 1. And then I'm isolating my y value, so I'll subtract 1 to both sides. And I get x minus 1 equals to 2y to the power of 3. And then from there, divide 2 to both sides. And I get x minus 1 over 2 equals to y to the power of 3. To get rid of that cubic root, I'm just going to, to get rid of the cube, I'm just going to root it by 3. And so I get left with the cubic root of x minus 1 over 2. And that equals to y. And so that would be my inverse. So I'm going to make sure that instead of using y, I'll use g of x. And I'll say g of x of the cubic root of x minus 1 over 2 is the inverse. Done. Okay. Finding the inverse of a radical function. Consider the function f of x equaling to 2 times the square root of x minus 3. Determine whether the inverse of f is a function, then find the inverse. So I'm going to start off again with graphing out a general sketch. So right here, if I have the parent function of f of x equaling to the square root of x, then I know that it's kind of like an arch when I have my image. And it doesn't seem like we have any reflections because there's no negative signs anywhere. I don't see a negative anywhere on our x or on the inside of the x or outside. It does seem like we are going to move to the left 3 points. So you can always move your image 3 points to the left as well. And so I could check to make sure if this is if the inverse is going to be a function, which it seems like it is because all the points intersecting end up just intersecting once. So I can write here that the inverse is a function. Cool. But if you can recall from the beginning of part 1, when we are dealing with radicals or squares, it's a little different, where we said that if our domain, at least for this one, finding the inverse of a quadratic function, if our domain is positive, that restricts us to having a positive y value as well for our inverse. So for example, for this one, we had here positive function. Our inverse had to have a positive y value. It couldn't go down this way because these y values were all negative. So that was the inverse of specifically a quadratic function where f of x is equal to x to the power of 2. Now in this case, right over here, we're dealing with radical functions. So we're going the opposite, where now we have a radical function and we're going to end up with a some sort of y equal to x squared. And so we still have to go based off of those rules and guidelines. So I'll write right here that because our range here, so the range in this area is positive, and it's not down here being negative, then our domain is going to have to be positive as well. Domain needs to be positive, okay? So I'll write over here, because the range of f of x equaling to 2 square root of x minus 3 is positive, the inverse domain has to be positive. To be positive. And we'll get more into that as we continue on with this answer. So let's start off first by finding the inverse. If we have here y equals 2 square root of x minus 3. I'm going to start off first by getting rid of the 2. That's going to divide 2 to both sides. And I'm left with y over 2 equals to the square root of x minus 3. And then to get rid of the square root, I am going to square on both sides by 2. That gives me y to the power 2. Oops, sorry. And I realized that I didn't switch the y and x value. So y equals 2 square root of x minus 3. And I need to swap it. So it's x equals 2 square root of y minus 3. Now I can do every single step that I did, where I divide 2 to both sides, and I get x over 2. And this becomes the square root of y minus 3. Then square it to both sides to get rid of the square root. And we get x to the power 2 over 4 equaling to y minus 3. From here, I'll just add 3 to both sides. Add 3. And I get left with x to the power 2. Change this to 1 over 4 plus 3 equaling to y. So again, my parent function here is going to be, in the end, y equaling to x to the power 2. So when I draw my inverse, I'll draw it in red. It's going to look like this, where I have like a U shape. But again, let's go back to what we wrote over here as a rule. We said that because the range of our function of f of x equaling 2 times square root of x minus 3 is positive, so the range is positive here, that means that the domain of my inverse function has to be positive. And the only time that the domain is positive is starting from 0, going all the way to the right over here. And so it's important that when I write my answer here, I have to write down that the inverse, and I'll move it up a little bit, the inverse of f of x equaling to 2 times the square root of x minus 3 is g of x equaling 1 over 4 x to the power 2 plus 3 when or where our x values are all positive. So this is the most important part, knowing where it's going to be located. So all the points starting at 0 where they're positive or greater than 0, which is this side. So I would erase this side. And that would be how my image of the inverse function would look like in the end. Okay? So it's really important that when it comes to radical functions and finding the inverse of quadratic functions, there are some restrictions that you have to write for yourself, no matter what. Okay, so now that we found the inverse of a few functions, let's try it out as a multi-step problem. So, question here asks us to find the inverse of a function that represents the surface area of a sphere. We have the formula of the sphere as s equaling to 4 times pi times r to the power 2. Then we want to find the radius of the sphere that has a surface area of 100 times pi square feet. So let's start off first by taking our formula. S equals 4 pi r to the power 2 and we're going to find its inverse. So from here, I am going to isolate my r value. So I'll divide both sides by 4 pi, and I get left with s over 4 pi, 4 pi, equaling to r to the power of 2. To get rid of that r to the power of 2, I'm just going to square root on both sides. So I need to move this a little bit. Square root to both sides of my equation, and I get left with square root of s over 4 pi plus or minus equaling to r. Now the only thing here is that we're looking at radius. So for radius, one of the things about radius is that it must be positive. So radius must be positive, no matter what. Whenever you're dealing with radiuses, they must be positive. So because of this, I am going to actually get rid of the negative sign and keep it just positive. All right, we finished the first part, which was finding the radius of a sphere. So I found the inverse and got my r value. Then it says here that we want to figure out the surface area, we wanted to find out the radius of a sphere with the surface area of 100 pi square feet. So if my surface area is 100 pi, then I can substitute that surface area into my s value and then find out what my r value is. So I'll take my formula, s over 4 pi equals r, and I'm going to substitute it into the s value, so that now I have 100 pi over 4 pi equaling to r. The pi's can cancel out with each other, and I get left with inside 100 divided by 4, which is 25. And 25 square rooted is just 5. So the radius would be 5 feet. So the radius of the sphere, is 5 feet. Done. Okay. So hopefully this helped. Good luck.